Okay, finally. Can you see my screen?
Yes.
Yep.
Okay. So, yeah, I think we've mentioned ARC-AGI various times before as an interesting benchmark. There have been two previous versions of it, ARC-AGI 1 and 2, and ARC-AGI 3 was released earlier this year, in the beginning of this year, and it's really more sensory motor focused than the previous two, and seems like a pretty interesting test bed. And so I just wanted to put together a couple of slides on what it exactly is, and then also I've been thinking a bit more over the past weeks on how would Monty's capabilities fit onto that. Is that an interesting test bed for us to use? So yeah, what is ARC-AGI? It's an interactive benchmark for studying agentic intelligence through novel abstract turn-based environments in which agents must explore, infer goals, build internal models of environment dynamics, and plan effective action sequences without explicit instructions. It's a lot of words, but I'll get into all of these in more detail later. It focuses entirely on evaluating fluid adaptive efficiency on novel tasks without avoiding language and external knowledge. And environments only leverage core knowledge priors and are difficult calibrated by extensive testing with human test takers. So humans can solve 100% of the environments. So it aims at a lot of the things that Monty should be good at, like being able to learn from very little data, infer generalized knowledge very quickly, solve problems, interact with an environment, and so on. And yeah, the authors say, to our knowledge, ARC-AGI is the only unsaturated general agentic intelligence benchmark as of March 2026. So it's also a fairly well-known AGI benchmark, basically.
What does the unsaturated mean?
In
Lot
the
of
sense that, oh, yeah, go ahead.
a lot of the benchmarks for the new LLMs that are coming out, like for example, there's something called SWE-bench, SWE-bench, that tests the agent on solving like coding problems and making sure that tests pass. But because these are public and LLMs are trained on like public data, we think that the LM saturated means that they're getting like really high performance, like 70%, 80%,
All right,
and it's not
that's what it
really,
means. So
yeah,
Yeah,
basically, they're solved problems, and people are just it's like they're worrying about the last 1/100th of a percent or something like that. So they're
right.
saying
yeah,
basically this is a generally unsolved problem benchmark.
That's
yeah,
correct.
exactly.
Okay.
And they're going to pretty great lengths to try and make it such that training on internet scale data doesn't help you solve those
Mm-hmm.
tasks, and that their tasks don't leak anywhere publicly.
Who is creating this code base? Is this there's a lot of work going into
Um,
this. Who's doing this?
so it's the papers by the ARC Prize Foundation. One of the big people involved is Francois Chollet, um, and or yeah, this guy.
Yeah, I
And
know.
as far as I could tell from the paper, they set up like a game studio to build this, where they had various game developers come up with these different games and challenges and put together like a whole process to build this
Okay,
benchmark.
well, it's not so important here, but it's curious, like who's paying for this, and what kind of organizations behind it. Um, I don't know if we know that,
Um,
but that's not important right now. But it's interesting to think about.
yeah, I'm not sure who's paying for it, but the Arc Prize Foundation is behind it, I guess.
And I guess there's a prize too.
Yes, there is a prize. So overall, I think there's a pot of 2 million prize money right now. It's not like you beat it and you get 2 million. It's more like first, second, third, fourth, fifth
Yeah.
place gets a smaller amount at different milestones. Um,
Got
and
it.
I think ARC-AGI 2 is also still ongoing, so it's still unbeat. So you can still also win prize money for beating ARC-AGI 2. Um, but I think that one is in the last year, this year. And I think, yeah, this one is, I think, end of October this year is one of those milestones where you could win some money. Um, Yeah, and so it's a formal framework for evaluating general intelligence as skill acquisition efficiency rather than task-specific performance. And I just put this tweet from Francois Chollet here too, because I thought it was pretty nice. It's not specifically on ARC-AGI, but ARC-AGI is aimed at measuring this. So he says there are only two honest metrics when it comes to benchmarking intelligence, novelty and efficiency. You don't need intelligence to solve a known problem. You only need memory. And you don't need intelligence to solve a problem via brute force. But to solve a novel problem efficiently, intelligence is the only way. And yeah, I think Monty is aiming at both being good at novelty and efficiency. So it's an interesting benchmark that exists. I'm trying to measure that specifically. Past challenges and performances. So there's ARC-AGI 1 and 2, and LLMs have gotten progressively better at them. They say that the challenge kind of encouraged two major breakthroughs. Two major breakthroughs improved performance under challenge. One was AI reasoning and then agentic coding. But yeah, then in the paper for ARC-AGI 3, they kind of highlight some issues with the first two, where yeah, benchmarks that are designed to resist direct memorization can now be attacked via higher level shortcuts if the public training set and the private test set are overly similar, like identically distributed, and the model was trained on an enormous amount of tasks representing a dense sampling of the task space. A simple strategy to achieve this is to ask a model to generate more tasks from the domain, solve them, verify the solution via a reliable verifier. Like AGI 1 and 2 were both verifiable. Then train on the produced reasoning traces in a loop. This can scale to millions of tasks, enough to provide high coverage density of the target domain at training time, thus considerably reducing or outright removing the need for test time adaptation. And so with ARC-AGI 3, they're really trying to make the test set be a totally different distribution from what is even visible publicly in any form or shape. And like making sure you can't just kind of hack your data set to be larger and then hope for it to generalize on the test set. Because that's not really true generalization if you're just densely sampling the distribution. And your test set falls within that distribution.
It's what's interesting is how this has been going on for decades, how people can be so clever in getting around benchmarks. It's like
Yeah.
it's amazing. I mean, clearly, that strategy, if I don't understand it very well, but that strategy clearly is it, it's getting past what the quote you just had from Francois Chollet. It's like it's cheating in some sense.
Yeah.
But it
And I
solves
guess
the task.
they collected good experience with the first two benchmarks on like how people try to cheat benchmarks. So trying to make this third one
Well,
capture
that's the thing
more.
about benchmarks. It's like
Yeah.
it encourages you to cheat. It says all that matters is beating the benchmark. So
Yeah.
anything doesn't matter how you do it. Okay, pretty
Right.
interesting.
Yeah. So yeah, going forward, benchmark designers will need to steer private data sets to be out of distribution from any publicly available demonstration data if they want to test true generalization. Um, and then, yeah, ARC-AGI 1 and 2 focused on data efficient modeling, so inferring rules from static input-output pairs. ARC-AGI 3 shifts to targeting agentic intelligence, where you basically interact and need to solve problems by applying actions and seeing how your observation changes when you act.
I thought that ones you showed me earlier that they seem to be that way. Were those ARC-AGI 3? I mean,
Uh,
few examples you've demonstrated in the past, you had to move things around.
yeah, that's ARC-AGI 3.
Okay. So previously that wasn't the case?
No, I think the previous ones, it was maybe more like IQ tests where you have to find a pattern and
Oh, I
then
see.
apply it to a new thing.
Got it. Got it. So this idea that you have a little moving agent is new to 3.
Yeah.
Okay.
So what is ARC-AGI 3 doing or measuring? It uses a set of interactive turn-based environments to evaluate a test taker across 4 core functional components of agentic intelligence. One is exploration. So in real-world environments, information is rarely provided passively. It must be actively obtained by the agent by interacting with its surroundings. So the agent needs to figure out the rules of the game by interacting with it in an efficient way. Random exploration isn't really efficient enough to beat this benchmark. You can't just take a bunch of random actions and then use all of that to figure out the rules. You need to efficiently interact to figure out the rules. Modeling, inherited from previous ARC-AGI generations. This is the ability to turn raw observations into a generalizable world model that can predict future states and outcomes. Goal setting. So a cornerstone of autonomy goal setting is the ability to identify interesting or desirable future states without explicit instructions. The agent must independently determine what to target based on its own intrinsic drive and environmental cues. And planning and execution. So this involves the strategic mapping of an action path from the current state to an identified goal. It requires not only initial accuracy, but also agility to course correct in response to environmental feedback and unexpected results. There are more things that are required to solve it. I'm trying to make a fuller list, but these are kind of the core things that they're trying to target. There's no time limit between actions or asynchronous environment changes. So it always waits until the agent provides the next action. And the reason they give is that it prioritizes offline reasoning over real-time sensory motor reflexes. So it's not like the kind of games where it's really just about your reflexes and how quickly you can hit the buttons to shoot your enemies. You can reason between actions that you take, and like response time isn't measured. There's a simple action space, so there are a maximum of 7 actions per game. And the reason they do that is that the complexity of the benchmark lies in the logic of the environment, not the difficulty of the controls. So kind of abstracting away complexities of a motor system. And the observations are 64 by 64 grid with 16 possible values or colors per cell. Sometimes you can also get a frame sequence for non-interactive animations. So it might happen that you press a button and then a short animation plays out. But when the animation is playing out, you can't take actions until it's over. And yeah, the core challenge in ARC-AGI 3 is intended to be reasoning rather than perception.
Viviane, you said that efficiency is a big thing, that they're focusing on novelty and efficiency. But if there's no time limit, how are they forcing the solutions to be more efficient? Or is that not?
Yeah, so it's efficient measured in the number of actions that you take to solve the tasks. So it's not how fast you take the actions, but how many actions you need to take.
Okay, so it's better to reason more than to take actions,
You're right.
random actions.
Yeah.
Well, as opposed to you could just do like, Monkey typing on a typewriter, just move all over the place all the time, see what happens. And I'm guessing it's saying they don't want you to do that.
Right.
Yeah,
Okay.
exactly.
Makes sense.
So there are various environments and different tasks, basically, different games. All environments need to differ significantly from each other, and existing games that are out there on the internet. Those are kind of the constraints that were given to their game designers. The games need to be human solvable, so they tested every environment on 10 humans, and at least 2 of them needed to solve all of the levels. And it shouldn't be possible to solve them by chance. So just taking random actions won't won't get to success in less than 1 out of 10,000 trials. There are 6 levels per environment, and usually the first level is kind of a simpler tutorial level to teach the game mechanics in an interactive way. Since there are no instructions provided, it's a bit simpler in the first level to kind of figure out how does this environment work, and then levels get progressively harder by combining mechanisms that are discovered throughout the levels. And it only relies on core knowledge priors, and they list objectness. So elements are perceived as coherent, persistent entities that can move, collide, or be occluded. Basic geometry and topology, so an understanding of symmetries, rotations, and elementary topology. Basic physics, like gravity, momentum, and bouncing.
That's interesting because Monty wouldn't know those things unless learned them.
Right, yeah, so you would have to kind of pre-train Monty on some other games or other things to learn these basic knowledge priors. Then agentness, so recognizing that certain objects act with intent and pursue goals. And they don't use language or cultural symbols, so environments never use numbers, letters, recognizable real-world clip art like flowers or keys, or cultural conventions like green meaning go.
What about, in the examples you showed before, there was like a power meter and there was like, the 4 arrow keys. Those seem to be priors. Is that, are they
Yeah, so
not?
the arrow keys were just for the human interface on the website. Like in code, you basically just give a number for which action number you want to execute, so number between 1 and 7.
But still,
But
uh,
yeah, there are definitely a few more priors, I would say, than what they list here, like basic game concepts like time limits and lives, like number of lives you have.
right, right.
Um,
Well, that's why I bet there was a meter. Maybe there was a life meter, but there's
yeah,
definitely a little, bars that got less and less, and that you could tell you. Those are things people know from playing games. Um, okay, they're not mentioned here, but
yeah. I made a list later on where I added a couple more things that I think are required as priors, but yeah, I think there is a bit more than what they write here. Um, One more slide and then I'll show some actual games to make it a bit more visual. So how is performance measured? That goes to your question, Rami. So they're counting the number of actions that are required to solve an environment, since that measures the efficiency. It measures both efficient exploration to learn and efficient use of models to achieve a goal. So you both need to, in the beginning, explore in a way that you figure out the rules of the game quickly, and then quickly apply those rules to efficiently solve the puzzles. And then the performance score is a relative comparison to the upper median human performance. So basically, a relative score to how the humans that were tested on that game performed on the game. They have some public environments available, 25, and those are supposedly easier than the private ones. And the private ones are out of distribution of the public ones and contain different mechanics.
so I don't understand this. So what does that mean? Like the testing ones, no one actually gets to see them. You
Yeah,
submit your agent, and then they come back and say how you did, but you don't get to see
yeah,
them.
yeah, exactly. Because otherwise people
Mhm.
can just train their model directly on the task. And
Right, right. Well, there's other ways. You could do it like, I mean, in the end, as a designer of an agent, you'd want to see how your system failed. So at some point, you'd want to be able to see the private ones and say, okay, maybe when they come out with the next generation or something like that, at some point you want to see like, I don't know how I failed. I need to. It would be very useful to see. Like, what if we solved all the public ones, did it in a really clean way, and they come back and they say you failed on the private ones, or there's no way to learn anything. You know what I'm saying?
Yeah.
I think that's why they have the semi-private ones, like a validation data set that you can use. You don't train your models on this semi-private, but you only use it to validate, and you can learn how your model failed. You're not supposed to train on it.
Yeah.
But I'm not sure you can
Oh, I
actually
see.
see the failures there. I'm not sure to see,
Hmm.
but
Well,
I
this is a
think
classic problem, right? Um,
yeah.
yeah.
Yeah. I think it would be difficult to like debug performance on a private data set or even the semi-private one, but yeah, you can just kind of test against their semi-private
I
one
mean,
with external
right, but
API.
you can use it if you're honest, you can use the public one to build an honestly good system,
Yeah.
right? And so, in theory, if you did an honest, like we did it the correct way, we didn't overtrain and all these things, and we do well on the public data sets, we would expect to do well on the private ones. But if you didn't, then you're hosed. And you're like, what did I get wrong? You know, like, I don't know what I did wrong. I mean, it's
Yeah.
something we don't have to worry about for a long time. It's just more like a question.
Yeah.
Okay, I got it.
So yeah, how do these look like?
Okay,
Just some examples.
before you show these sets,
Yeah.
they were like, you said there were different, like, I forget the words you used. There were different tests, and each one had multiple levels,
Yeah.
right? And the different tests had different rules. So if I run one of these tests, I had learned a set of behaviors and rules that apply to this different levels. But then when I go to the next test, they're completely forgotten, and I have a totally different set of things. Is that right?
Yeah.
Okay.
Like normally every environment has a different test
Environment, right?
goal,
Right.
different way you interact with it, different
Different
look.
objects. But within the
Yeah.
levels, once I understood what the yellow blob does, maybe it does the same thing on the different levels.
Yeah, exactly. So I can
Hmm.
just show some examples to illustrate that a bit more. So here's a pretty straightforward one. Um, so in the web interface, you have these buttons, but you like in the API, you just give some numbers for the actions. And here you have up, down, left, right, and you can just experiment and quickly you figure out that clicking these buttons moves this block here. Um, and the thing that you then need to infer is that you want to go here, but you want this shape to match this shape. And so there's one more thing that's in the environment, which is this white thing. So you can explore what happens when you go to the white thing. When you go there, you see, oh, it rotates it. Um, and so now the orientation is the same. And now we can go here and complete the level. And then this is when it gets more complex. So that was basically the tutorial level to figure out the game mechanics. And then in the next level, we learn about one more concept, which are these yellow things. Right now, we don't know what they do. So I can go down here to rotate this shape again. It's not correct yet, but let's go to yellow. Oh, it fills up this life bar that has been decreasing with every step we took. And that's kind of something that to efficiently infer that, it's good to have pre-knowledge of these health bars from other games.
Hmm. Hmm.
Um, and so we can press this button again and again to rotate it in the right orientation. And go here, and then we get the third level, which is probably a little bit more complex again. So I think in this level, you have to change the color as well. So it kind of gradually introduces more complexity with every level.
Hmm.
I'm not sure actually what these things do. I think if I go up, they push me to the wall or something like that. Yeah. So that's another kind of behavior that's applied to the agent. Just to show a bit more the variation. So let's see what else we have. Here's one, for example. very different controls. This time you don't have arrow keys, but you click on locations. And so you just do an exploratory click. You see, oh, I clicked and this thing moved where I clicked. Okay.
So you said there's only 7 actions, but then this is an action at a location, right?
Yeah. So the actions are up, down, left, right. A special action, which is spacebar, and they're
But you're not doing up,
click.
down, left, right here. You're just moving the cursor around XYZ, right?
Yeah, and so click is the fifth or sixth action, which applies
But
to a specific location. And so
right.
there you specify action 6 and the location where to apply it to.
Oh, I see. So you're actually not moving a cursor. But you have to specify a location to do the action.
Yeah. So I mean, when I'm playing it now, I click, but if you interact, like if you code it, you'd say at this pixel, click. And
Hmm.
then in this case, it changed the color here.
Hmm.
Again, this is a bit of a prior for like if you played other video games, that if the color changes, you selected something and now you expect the behavior to be different. And so now this one is the one that's moving wherever I click. And then again, a lot of the goal inference is often about matching two patterns or two colors to each other. So here's like a purple circle and a purple circle. And so I infer that the goal is to put the purple circle inside the purple circle. But that's, again, a bit of kind of inference from my side based on existing models. And then, yeah, that was the tutorial level. Then it gets more complex. See if like the middle one gets into the wall, it can't move there. So you have to kind of plan on what's the path to take to get these into those shapes. And now there are 3 on there. So there's some spatial planning involved. And so, yeah, you see how this game is very different from the other one, both in controls and the goal and the looks and the skills required. Uh, see if there's something
How
else.
long before these are interview questions on the job interview questions?
See if you're an LLM.
Yeah,
Are you smarter than an LLM?
not a bad idea for filtering out. Well,
Filtering out AI.
yeah.
Yeah.
Well, in that last one, it was interesting because they have this in this 64 by 64 grid. Is that what it was? 64. Um, they're clearly it was like those were lines. It's like it's a weird. It's like I don't know. I have to think about how to express it. But we don't visualize that as a 64 by 64 grid. In our brains, we're using those as lines, and we're getting past the noise uh, of the of the grid resolution. In some sense, it's like would we expect Monty to say, "Oh, I'm modeling a 64 by 64 environment," or do you expect Monty to say, "I'm modeling lines in space"? Um,
Yeah. Yeah, I guess you still would want to do a bit of perception on this grid and detect lines and sh shapes
right,
and what is
right.
the outline of the agent and of the target and stuff.
In some sense, I felt like it might be easier if it was not so pixelated. Like the pixelation might make it harder. Um,
I mean, I think it should be still easy to detect lines and shapes in the
Maybe,
pixelated
right.
version.
All right.
But yeah, this one is like there you have the idea of gravity that in this case gravity is up here, like you fall upwards. But uh yeah, basically this one has a mix of moving the buttons and clicking to destroy these green boxes. Um and then again, more things are added that you have to figure out what they do. Uh There's some more complex ones for figuring out what goal you actually need to accomplish.
Quick question.
Yeah.
Now, I noticed it's a 64 by 64 grid, but you actually were you scrolling through the map? So like the actual underlying world was bigger than 64 by 64? Is that did
Yeah.
I see that correctly?
Yeah, in that case, yeah, the world is bigger than that.
Okay, thank you.
Interesting.
Yeah.
Here too, it's interesting just the fact that these controls are highlighted or grayed out is prior knowledge too, right? It's telling you what options you have available to you, what they mean.
Yeah, right. And I'm not sure how the API works. Probably if you try one of these, they don't count it as an action. So at first you could try them and then know which ones are valid. But yeah,
But
I'm not sure.
even the concept of reset. Okay, just the concept of, well, okay, what if there isn't a button? There's just a command that says reset. Well, that's still a concept. That's a prior knowledge.
Yeah.
Um, hmm.
We talked about like
So
state space modeling for tasks and stuff like that before. So, the idea of a reset moving you back to an original location in state space or task space or something like that, I guess. Would
Yeah,
be
but if you think about Monty or learning modules, do they have any concept like that? I don't think they inherently do.
well, once we implement object behaviors, we would have the concept of things being in different states. And
Right,
so
but
then,
is there a concept of the reset state? I'm not sure there is.
no, reset would be more like an action that takes you into a specific state. And in this case, it would take you into the first state.
Right. But I mean, there is in a game that's sort of I'm just saying this, I still think that's prior knowledge, understanding that
yeah.
there's a game and it begins and they can go back to the beginning of the game.
Yeah.
The world's not like that. So
Yeah, I mean,
it
it's
just
definitely something that would have to be learned, that reset takes you back to the first state, the very
mm,
first observation that you saw, basically.
but a human wouldn't need to learn that. They see the word reset, contrary to what they said earlier, that they're not using any cultural things, but the word itself, it tells you what it does.
Yeah, I
Just
mean, they would have needed to learn that at some point in their life, but yeah, when they come and play these games, they come with that knowledge.
that's prior knowledge that they said they weren't
Yeah.
going to use. They weren't going to use it. There it is.
Yeah, I agree. There's definitely some more prior knowledge than what they listed there.
Right.
Um, but yeah, so here you have to then infer that all these red ones kind of make the same shape that's shown in small here. And so now you're supposed to make the shape here. Um,
Hmm.
and then it gets a bit more complex because it needs to be combined and you have different colors. We can go back to these and go through the different, like they are all different from each other. So just showing brief.
Each one was designed by a different game designer. Is that the idea? That they
Yeah.
all okay, so yeah.
And I mean, maybe some had the same game designer, but basically the team internally would make sure that they're all significantly different from each other.
But they didn't no one sat down and said, let's design these 10 games to be this. It was like different teams came up with their own ideas and they make sure they weren't too common. It just makes it harder because there isn't one person thinking about all these things.
Um, so I think it was a team of game designers, less people than there are games now.
Oh, I see. So maybe
And
they all did get together and say, let's do a game like this and let's do a
yeah,
game like that.
right. I think
Okay.
like every game designer would propose a game and design it and then run it by their colleagues, and then they would test it with humans and with like
Yeah.
test subjects. Not that
Okay.
they're not humans, but
But
uh,
there's definitely no order to these. It's not like these tests, they get harder within the levels, but not within the games. Is that correct?
yeah,
Right. And not within the environments.
yeah.
Okay.
Um, and yeah, they all have kind of different mechanics and different ways that you need to solve them. Um, so briefly, what are current approaches? So just what they had in the paper, running the current state-of-the-art models on there gets a very low score. Um, it all is very LLM focused, all the approaches that I saw. So is the benchmark. Like in the paper, they basically say the system prompt is you're playing a game, your goal is to win, and so on. So basically, the fact that they are giving a language prompt kind of shows that they're aiming it at people who use LLMs on this task.
Those scores on the upper right, are those, how do I interpret 0.5%? What does that mean? Do you know?
So I think 100% would mean that they had equivalent performance as the human subjects.
So these are very low scores.
Yeah.
Okay.
So
they're not even,
Anthropic is 50% or is it 0.5%? Like is one perfect score or 100 perfect score?
oh,
I think it's 0.5 as far as I understand, but
so that would be like really, that's what I was saying. Thanks for trying to clarify that. I was thinking like, yeah, is that like 50% right? Or like 0.5% right?
yeah, let me double check. So I mean on this line they showed up to 100%, but then let's see. I think it goes up to 100%.
Wow.
So where they found that on some of the games they could actually do quite well with very specific LM harness, but then overall it was 0.5.
Yeah, I
Oh,
see it on their
interesting.
blog. Yeah, humans
So,
score 100%. AI
so
0.5.
some games environments that could be solved and some couldn't. Hmm.
Yeah, and I think the ones that they could be solved were kind of the outliers, because otherwise the overall score wouldn't be that low.
So the reason we started looking at this is Vivian and I was sitting around chatting, and we were saying, are there benchmarks that no one has been able to solve that, because we don't want to be out there competing with LLMs. We want to like find an area where the differences matter. And Vivian brought up ARC-AGI. So it's important. We really want this to be a really, really hard problem for deep learning networks to solve. Otherwise, if they could solve this problem, then we wouldn't, even if we could solve it, it'd be great for us, but it wouldn't generate any attention, you know.
Yeah,
If we could
yeah,
do 10 times, if we could do 10 times better than any of these guys, that would be worth a lot.
yeah. So as far as I know, none of the submissions since the paper came out have solved it. Yeah, the top one is, I guess, at 8%, 7.8%. And yeah, I think this one is just a public leaderboard where they actually say you shouldn't take this as an indicator of solving it because you can still cheat in some ways. The real one is only if they submit it to their milestone competition on the very private data set.
Mm.
And that one, yeah, I think will be announced towards the end of this year.
It's important that we be able to solve problems that other systems can't. Otherwise, what's the point of this, right? So whether it's efficiency, and I'm sure there should be, right? I'm not questioning that, but it's so hard to find benchmarks which aren't tuned for what people can do. So
Yeah,
that's why this is such an attractive one for us.
yeah. So how about Monty? Um, so what are the kind of skills that are required to solve ARC-AGI? You need to be able to learn continually from few examples. Monty can do that. You need to be able to learn without supervision. There are no labels provided or anything. Monty can do it to a certain extent, but isn't great at it yet. You need to select actions to maximize learning speed and develop and test hypotheses about causality. So Monty can act reasonably well to learn efficiently in the kind of settings that we currently have. but not really in that ARC-AGI environment and not really to test hypotheses about causality. All of Monty's policies right now for learning are focused on exploring an object efficiently and not about interacting with an object to figure out how it works. By the way, everything on this list are things that we eventually want Monty to be capable of. That's just the current state.
Well, yeah, right. I was thinking about the causality. We've had a lot of conversations about causality and the mechanisms behind it, which to me is the first and most important step. But then to make the system want to discover causality is work, but it's not in my mind, it's not a fundamental. It's something you have to add as opposed to like, oh, we have no idea where to begin, type of thing.
Yeah.
So we're trying to expose the things we have to do here, right? But these aren't things that we're like, oh, I have no idea how to do this. At least not yet. Maybe I'll come up with in a minute.
Right, yeah. A lot of these will be things that we have ideas how we want to do it. We talked about them before, but we haven't implemented them yet. Some things like, I mean, how to test causality, like how to come up with a hypothesis about causality. I'm not sure we have talked about it too much yet. We mostly talked about how do we learn causality after we observe something causally happening. But isn't an impossible problem. Then, yeah, we need to be able to represent state changes in an object, including different available actions in different states and behaviors. That's something that Monty should be able to do once we implement object behaviors. It needs to be able to infer and learn causality, learn object interaction behaviors, so how two objects can interact with each other.
Is that different than causality, or is it
Um,
like one? Because the way we've defined causality in the past is it's a behavior of one object invokes the behavior of another object. It's in various ways.
yeah, it definitely requires causality. Not sure if it requires
It's just the link.
inference.
Causality is the linking of two behaviors.
Yeah,
So it seems like object interactions of objects is just a form of causality then.
yeah.
Maybe like
Um,
maybe saying learn causality. It's like it already has to have a notion of causality just to be more, I
It
don't know,
just it
explicit.
has
It
to,
has to learn these specific causal relationships in this game, not
but
causality itself.
well, yeah, I think, but we defined basically once we had behaviors, then causality is just the linking of two behaviors.
Right.
And we can link them at the beginning, you can link one to the end, you can link them at different points in behaviors, but it's just the linking of two behaviors. And that can be observed. And it's across objects, it's across modalities, it's just like, hey, I have a behavior here and it's simultaneously or precedes a behavior over here, and then you just link them together.
yeah,
So
yeah. I think you're right. That's what we kind of concluded that yeah, object interactions is just causal link between two behavior models. Um,
so I'm not
where
quibbling with your words here, but some of these are overlapping. Some of these are
yeah,
similar.
right. Then we need to be able to use the learned models for planning and reasoning, including readjusting plans based on feedback. So right now we're using our learned models for planning movements to do inference faster, the hypothesis testing policy. But this challenge is really a lot about actually achieving goals and making plans to achieve goals and getting in a specific state, which is going to be a lot more involved and also needs to involve the causal connections that are learned for planning. Then this is a tricky one where I'm not sure yet how to do it in Monty. It needs to be able to infer goals, so there are no instructions provided. Often it seems like the goals are based on pattern matching, but some way to infer what the goal is.
I thought when the first environment you showed where you had the little box in the lower left-hand corner that and it was like they showed the orientation that the object had to be in. That seemed really tricky to me. I think that's
Yeah,
what you're talking about here. Like there was a
yeah,
section of the environment that really wasn't part of the environment. It was you couldn't move there. It was just like a little symbol off to the side, and you had to say, "Oh, I recognize that's a symbol. I see it elsewhere. I see the other one rotated." It's like, and it was larger too. I noticed it was larger, and that's was a clue. That was a prior clue saying this is larger. It's probably not like the other things in the environment. Um, it's like a little window off to the side. So that was like tricky.
yeah.
And that's what this is. Like you had to somehow recognize that thing over there is not the same as the other things, and it's a symbol, and I see the symbol elsewhere, and that's a tough one.
Yeah, I think if I had to pick one off this list, we have the most uncertainty about it, it would be this one on how
Yeah.
Monty would solve that or how we solve that. It seems like there are again various priors that we use and experiences from past puzzles or games.
Mm, that does seem right. It does seem there's a bunch of priors in that.
Um, then yeah, I need to be able to recognize objectness and segment objects. So be able to tell what belongs to the agent or an enemy or the goal or something that blocks your path. Um, and yeah, I guess Monty has a concept of objectness and occlusion and stuff like that. Object segmentation is something that Scott is currently working on. So Monty's on the path there. And then it needs to understand symmetry, rotation, and elementary topology, things like inside and outside, and connectedness, holes, stuff like that. Monty understands rotation. So that first game I showed, understanding that this one object is the same as the other one, but rotated, should be able to do that if we disregard scale for now. But then yeah, symmetry it can also understand, but it, for example, doesn't have a concept of mirror symmetry right now. Um, and yeah, I guess elementary topology might be something that's related to abstract models of more concrete models, but I'm not sure. Yeah, speaking of which, abstract models and generalization, so similar representation of board as a goal state, like you just mentioned, Jeff. We're also in the last task I showed where the goal was in the center pixel of the outline. And yeah, things
Is
like
that an
quality.
abstract model? Is that I don't know how that's an abstract model.
It depends on how you define abstract models. I'm more phrasing it as like a way to generalize very quickly. So you've seen a pattern once, but then you can infer that it's still the same pattern, but it uses different colors or is a different scale or slightly different
Yeah,
style.
I guess I would prefer if you didn't use the word abstract models here because I thought to us abstract models were models of things that don't have any physical presence, and or it's difficult to
Yeah,
say what the physical presence is.
no, they do have physical presence, but they are a bit more removed from like the direct sensory input, I would say. They're less about the specific color and stuff, but also th concepts like equality and incrementing and decrementing something
Hmm.
I put in that
Well,
category.
there's a lot of things. I guess just the general, when I've used the word abstract models in the past, I thought we have two. It was things like democracy, where you couldn't say anything about what it physically is or its relationships are. We didn't really. I'm just saying I agree with everything in the sentence except I don't know, but using the word abstract in a way that we haven't used it before. I think, but
Yeah,
it's not a
maybe
big deal.
if I call it
Just
categories.
yeah, just don't call it abstract. Just reserve that for this unknown boogeyman.
Yeah. Um,
Yeah, that sounds better.
okay, then we have understanding basic physics like gravity, momentum, and bouncing. I made that gray because it might be a subset of object behaviors, where learning about gravity is just another behavior model that you can apply. Maybe it's something distinct. understanding agentness and goals in others to predict their behavior might also just be another behavior model.
Is that I didn't see that in the environments you showed. Are there
Yeah,
environments
I can show an
where you're
example.
competing against some other little, agent that's
Yeah,
running around?
this one is not competing, but it's collaborating. So okay, so this is just a tutorial environment. You basically have to walk up to one of these blocks, and then you have to press the space bar to pick it up, and then you move it into this target zone.
Hmm.
So yeah, that's the first mechanic you need to discover. And then now there's another agent, this orange one, that does the same thing. And it also picks up these blocks and moves them in here. And you can basically, at first I wasn't sure if I'm competing with this agent or collaborating, but yeah, eventually it seems like, yeah, you are collaborating with him. And so you can try and
So
get the one that are
it
furthest
doesn't move
away.
unless you move. I mean, otherwise, why don't you sit back and relax and let it finish the job for you?
Yeah, it
I guess
doesn't move unless I move, and it's about efficiency. So you want to
so.
get it done as quickly as possible. So now I
Hmm.
probably didn't act optimally because I'm in this way, and I don't know.
Hmm.
Uh, yeah, this wasn't a
Yes.
great example. And now he's
No.
just taking it away from me and doing it himself. So yeah, when the
Oh,
AI
that's
is
pretty funny.
more smarter than you. But now in this one, I actually can't cross this boundary here, and the target zone is on the other side. So
Oh, I see.
now I
Right,
need to
right.
bring this agent my blocks so he can put them into the target zone. And so, yeah, in that sense, you have to kind of figure out other objects' behaviors or agents' behaviors.
There clearly is prior knowledge here, like this could be a room with a wall, right? I mean, there's lots of other colored things here. Just the fact that there's a gray line doesn't really tell you what it is, but the fact you can't move into it, you can't move across it. I mean, there's prior knowledge about the idea of wall and permanencies of walls and things that you can't pass through.
Yeah, right. Yeah, there are definitely these kind of basic priors in there.
Hmm.
It seems like in that case, there was even potentially some visual language. In fact, I've seen a few instances of that, like the brightness of something might have something to do with salience. The slashes across it look like caution tape, so we have some priors about that's a
Hmm.
barrier. But there's a lot of
That's a
subtle
good
visual
point.
design.
Although I suppose if I saw this gray, that helps still. But I suppose if I just saw that gray without the slashes, I'd probably figure it out, right?
Yeah.
But interesting. What's the difference between the black and the gray squares? I mean, I assume I can't go through the black ones either. Oh, I see. The gray ones I can deposit something in. The black ones I bet you I can't do anything with.
Yeah, and it
Um,
separates the agents. So now in this one, for example, this one has exactly 3 target zones and these two have 2. So I have to give them the right amount of boxes because they couldn't walk into each other's
mhm,
fields.
mhm. Interesting.
And yeah, I guess at this point I just walk in circles and let them do their job. Oh no, actually I think yeah, I didn't count the boxes and gave this one 4. So yeah, that's exactly the issue there. Um, yeah, and then this one starts walking. So yeah, that's the
Mm.
extent to which and then I think there's another level where you have like enemies you need to avoid, kind of like in Pac-Man, where you go through a labyrinth, but they face in a certain direction and you shouldn't walk past them when they face in that direction. Um, yeah, so that's that. But again, I think it might be also solvable by just the basic behavior models and assigning those to those agents.
Mhm.
And then, yeah, knowledge of basic game mechanics, like clicking objects to select them, things that are likely clickable. Like if you're initially exploring, it'll be very inefficient to click everywhere on the screen to figure out what's clickable, but we have these kind of priors of this is the most likely object I should click on, time limit and life, things like that.
Yeah, before when you were noting the object orientation legend, the health bar that you mentioned also was another. It's an artifact that's in the 64 by 64 space, but as Jeff said, isn't part of the playing field. It's a meter that's giving
Was
you,
it? I actually was it in the 64 by 64?
yeah,
Or oh, it was okay.
it's not part of the control panel.
Uh-huh.
It was part of the game. That the
Interesting.
concept of using up energy or something and depicting that as a thermometer is quite a
Yeah,
complex prior.
yeah, yeah. It's definitely something that we immediately pick up. It should be something that Monty, for example, should be able to pick up relatively quickly too, like basically just learning the causal relationship that whenever I move, this thing down there is going to change its state. But it would
But
take
even
a bit
just
longer to
it
learn.
almost looked like a Game Boy or something like that. You know, it's like you could see they clearly had like, oh, here's the a outer box, you know, there, right? There's an outer box, and then the screen is in the black section in the middle.
Yeah, I mean
Oh,
in the
okay. So
API, the agent would the AI would only see this part.
I see. Yeah, right, right. All right. So in that case, I see what you're saying, Dale. The yellow bars are inside the play area.
Yeah, and even the three dots, which probably are lives.
Yeah, I
Yeah,
think these
I
are
was wondering
live.
about I guess that too, right? So there's a prior to that, right? And then also the way they show the icon on the bottom left, as I was saying earlier, it sort of it sort of suggests it's not part of the playing field, and it's larger. So right away, you don't think that's something you're going to interact with. At least initially, you don't think that. Um,
Yeah,
And topologically, it's not reachable. If you
uh,
if you
right,
understand that.
right. So the light gray area is the room, if you will, right? Yeah,
yeah. If you understand the concept of walls.
yeah. There are a lot of priors and a lot of game-like priors here, right?
Yeah,
I mean, they make it a lot easier by putting it in in that little Game Boy sort of frame, so that I can. It just makes it clear that the yellow things and the red dots are lives and energy.
Tristan?
Yeah, there's, I think, back to the list of the things missing.
Yeah.
Is it required? Is this the full list that you have so far?
Yeah,
So one thing that I don't see on this list is modeling a 3D world, because most of these examples are a top-down view. All of us interpret it as top-down bird's eye view. We're talking about walls and barriers and whatever. That only makes sense top-down. I can't imagine how you would model this without a 3D world. And furthermore, I wonder if some of the auto distribution games are actually 3D first person view. Um,
Well, they've defined it as a 64 by 64. So
Grid, but we had an example of a world scrolling past your window. So it's actually a 64 by 64 window, not a 64 by
I see.
64.
So maybe you go through space in the third dimension. You're saying,
Right, like maybe you have like a
yeah.
first person, like I'm going through a labyrinth and I'm just seeing the pixels as if I was in the labyrinth in the 3D space, as opposed to top-down view, which is all the demos are here about top-down view sort of
Mm.
thing.
So Tristan, I'm not sure that top down is the only interpretation. What if you think of that as a 2D world, right? That you're operating in 2D space and barriers are still barriers. Common color was reachability.
What
You know,
the reason it's a top-down view, I already seen a counterexample, which is you can't see through walls, but you have God's eye view of the entire scene. So if you
That's
try to
true.
inhabit any particular agent, you might never solve the problem because it's opaque to you.
Yeah.
Another interesting thing is I was taking what you said, Tristan, and I was saying, well, imagine if instead of I'm viewing it like you're right, you kind of view it like it's lying on a flat plane and you're looking down on it. So I said, well, couldn't I imagine it being vertical plane? And then I said, oh no, because then I would expect gravity to play a role, right? And if I saw gravity effects, I would almost imagine the plane being vertical. It's like just an interesting observation.
Yeah,
Um,
but I feel like, yeah, I think you could still learn to solve these games without modeling it as a 3D world. So you can learn that you can't walk through the black colored blocks
right.
and stuff like that. And I mean, for example, in the one game with gravity, the gravity was actually inverted, so things would fall upwards. And
Yes.
you could quickly learn that too. Like you just see the causal relationship and figure it out. I mean, I
I saw
think
that.
when it
I saw
follows
that
our
as a
3D priors, it helps us infer it faster, but
uh,
yeah.
when I saw the thing go up, I thought, oh, it's like a helium balloon.
The,
Gravity's still going down.
I mean, another reason I want to mention that is because what if some of the games have four-dimensional mechanics? Um, and things like that. Although it said humans can solve it, so I don't know how many humans can solve. There are, I've 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 seen a game that uses space in four dimensions. It's like 3.5 dimensions, which is kind of weird, but humans are playing it, so humans can figure it out. Um, where four dimensions is a shadow in a three dimensions. But the reason I'm bringing that up is um, because again, the benchmark is humans can solve it. So I can think of no human who looks at any of these game boards and imagines I'm in flatland, I am that square. No human, I guarantee you, no human solved it that way.
Really? Don't
Uh,
you think when you play like Tetris or you play games like, Pac-Man and stuff, you don't think you're thinking of it as 2D? I
No,
do. I think
yeah,
of it as
yeah,
2D.
you're watching a 2D screen in three dimensions.
But I don't
You're not
model the
viewing it from
game
the
and
perspective of the piece, is what I'm saying.
right.
so I
Um,
think the reason I think they won't that I mean I don't know what the hell dot games are, but the reason I think why I would think they wouldn't be 3D renderings of a maze is because they explicitly say that they want it to be focused on reasoning rather than perception. So it would be kind of weird if they added things that require 3D perception.
yeah.
But I mean, that doesn't mean there won't be mechanics that we interpret as 3D, where you like go into a hole and you get out in another hole or whatever, or you go up a level and down a level or something like ladders or whatever. I'm just saying, yeah, maybe it's still solvable with just state changes and causality.
But I guess what I'm trying to say is, because efficiency is one of the goals, right?
Yeah,
And these games are designed by humans,
yeah,
and humans think in 3D world. Therefore, having a 3D prior bias might help you interpret all of those things as a human would, which is 3D objects and, you know, looking at objects 3D from above. Like that might be a powerful bias. And it
yeah,
seemed to work majority of those things.
yeah.
Mm.
Yeah,
So yeah, I added, yeah.
that third person perspective, Tristan, was very important.
Um, yeah, so I played the first levels of all the public ones, and those seemed like the ones that were most required. But yeah, there might be other things required on the privately held out ones, but it might be other things that we're not thinking of right now. But just on a high level, like what's missing in Monty, we're still missing the full capability to model compositional models. We would need to have that to learn temporary arrangements of sub-objects, the environment composition here. modeling.
So that's, by the way, that's just worth pointing out. We focus a lot on compositional models, like static compositional models, like the logo and the mug. But this is more like the ones that's like the intersection I talk about a lot, right? Where we're continually just building compositional arrangements, even temporary ones. So
Yeah.
we remember where was that yellow blob a minute ago, that kind of thing. So this immediately throws us into the fast learning, which I like. It's like, I don't know if there's any examples there where you had like logos on mugs, but there are lots of examples of like, where are these different parts right now? And I have to remember that.
Yeah.
There was a visual indication of which direction you're facing as an edge on the piece you were moving.
Yeah.
That I felt like was a logo on mug kind of situation where the orientation mattered.
Well, the orientation mattered, but was it really compositional? Like I said, did you say, oh, there's a yellow bar. I know the yellow bar, and there's a gray square. I know the gray square. Oh, look, they're combined together here. Or is it just
Right.
an object that was a gray square with a yellow bar? That's how I viewed it. It was
Possible.
an object that had an orientation, but I didn't view it as composed of two objects that I was familiar with from before.
Right, but that helped you understand that orientation mattered and you had to face the object to pick it up.
Right, right. But composition, what we're talking about here, Dale, composition is when you have two models that are combined together. Again, it would be like it'd have to have like I don't know.
Yeah, no, this could be a stretch,
Yeah,
but you were talking
yeah,
about affordances before and grippers and gripability.
yeah. You don't have to have composition to do that.
Oh, okay.
Composition is really an arrangement of two other models relative to each other.
All right.
And a model itself can have orientation and have lots of features on it, but it's whether it's composed of sub-objects.
Yeah.
And in this case, you could this whole game board is like the intersection I see out of the coffee shop. It's like, okay, there's on a particular environment, you've got some arrangement that's sort of permanent. That's a object model of the environment, and then you have child objects that are at different points in time, different places within that. So it's I'm not disagreeing with you. I'm just saying that in this case, the most of the compositional stuff that Viviane is showing and talking about, it's really the dynamic composition, things that you just learn temporarily, like the intersection. Right now, there's a red car at this in lane, and a moment later, it's a green bicycle.
So when you pick up the block and you move together, is that a composition?
Only if it's permanent. I don't know. That's a good question. I don't know. It might
Yeah,
be.
I guess it's temporary composition because now the actions move both of you together.
Right, right. So there is definitely composition here. It's more
Yeah.
like, right, but almost all the examples, that's a great example. Almost all the examples are still temporary compositions.
Yeah. And then, of course, we also need composition to assign behaviors to objects. Like let it know how you can interact with objects. Which is, yeah, the second one, object states and behaviors. Then need to be able to infer and model causality, including hypothesis development and testing, infer and set goals, and use the learned models and causality for planning, categories and generalization to some extent, object segmentation to a basic extent, like based on borders and movement. And then potentially these are kind of smaller ones, which is mirror symmetry, connectedness, holes, basic physics, which might be pre-trained behavior models, agentness, and scale. I think scale is a definite now looking back at the experiments, at the games. Oh, and Python 3.12 support.
Which part of these doesn't belong? Can you explain that? I mean, maybe obvious to everyone else, but
Just if you want to run their ARC-AGI package.
is that not what we run? We run a different Python, or I don't know what that means. Like,
We run Python from the before times.
so we would have to upgrade our version of Python to be able to work with this. Is that what you're saying?
Yes.
Okay.
Yeah, Jeremy's working on it.
Our end of life end of life for a Python version was like 2 or 3 years ago. Yeah.
So,
Oh, yeah, 2024. Yeah, 2 years ago. Our Python
so,
expired.
so how are we still able to run
Uh, with with
unsupported Python?
with a lot of yes, with a lot of uh, what's the word I'm looking for? I don't have a good word for it.
Trouble.
Stick-to-itiveness.
Okay.
Determination. With a lot of
That's
determination, we continue
there
to
we
run
go.
3.8,
Okay.
but we're getting close to getting boxed in where it becomes difficult, and Jeremy's getting us out of that box, fortunately.
So yeah, another important thing is what's not important in this benchmark. So it's really a problem-solving focused benchmark. It's not perception focused. So a lot of our object recognition problems don't apply here. It's not 3D, no 3D related topics like distortions and stuff. No need for efficient policies, like to recognize things because we can just process the whole image at every frame. And few other efficiency issues like multiple learning modules, voting, top-down connections, inductive biases for hypothesis testing, or sparse models, because we don't really have a compute or memory constraint here. You have infinite time between actions to analyze the frame, look at every pixel, integrate all the information. Compute is like Monty is so much below the compute that LLMs use on this. It's not really a concern here.
So
And
Would
so the
you?
hold on, I feel like I registered strong disagreement that the first two are important. And I haven't heard a counter argument saying that we don't need 3D related. Like, can you explain why the first two are not important?
I meant more like things like the logo wrapping around the cup and like things distorting in 3D space and
But I have to like
like
project a wall into 3D space
Do
if I'm
you?
imagining things from looking top down.
You when you see that you imagine the wall being a 3D wall? Is that what you're saying? I'm confused.
I mean, barriers, yeah. How do I like if it's a passable barrier, I can just it's a line. Like just imagine a line painted line. I can just walk over it. It's not a real barrier. But if it's a vertical wall, then I can't walk through it. What's the difference
uh,
between the two?
But
It's
you
on
three
can infer,
dimensionality.
but
or
can't
is
you
it, or is
quickly
it?
infer that you can't walk over the painted line?
But I can.
Well, I don't know. Is that really? It's funny because maybe you perceive it differently than I do. I don't perceive it as. I just say, oh, there's some lines you can't cross, and there's some lines you can, uh, and you have to discover that. You then a priori, after the fact, you might say, oh, I'm imagining as a wall, but there's nothing wallness about it when you look at the image, right?
I
It's just,
I guess I'll make my objection conditional on a thing, and the condition it is on is if we're because I'm trying the entire time I'm trying to think is like how we're gonna build a Monty to do this, right? And the Monty is the player of games here. The Monty is human. Monty is not that agent in that world moving. So that's like my it's
Yeah.
my bias.
right,
I mean, we don't have to
right,
solve
right.
it that way,
Yeah.
but it's a
That's
player,
correct, right?
and
Yeah.
so I as a 3D human, I just have hard time imagining seeing a 2D land. Like you can't see a 2D land from 3D, like without third dimension. I can't like
The question is, how are you modeling it internally? Um,
right. But it's like just the novel flatland, right? Like you can't imagine like there are certain things that are impossible in 2D that only make sense in 3D. Like the circle versus the sphere story and whatever else. Like you can cross boundaries in 3D. You can imagine crossing a boundary in 3D that is literally impossible for you to model without a third dimension in 2D.
Yeah,
but
but it
Like,
Yeah.
like maybe a closer example to what we've seen, a porous boundary. Where can a thing cross and I can't? Like that becomes hard, like becomes even more difficult to imagine.
Well,
But it
I
just
guess
seems like you can easily infer the rules of the boundary. Like even if you don't have a 3D interpretation of it, of like maybe this is just a small wall or something that I can place the box on. You still
right.
quickly infer the rules of the wall. You try to walk through it and then you notice, oh, I can't. Like it's not like I
I,
see that crossed out wall and I think I
I can
can't
think of a
walk
lot.
through it. I tested
Right.
it.
I can think of a lot of rules that don't have a 3D equivalent. Like I could say, oh, you can only push this thing through the wall if it's at a certain orientation. Well, that doesn't make sense in the physical world, but it was easily learnable in this world. So, well, I don't think we have to resolve this issue now. There's so many other things to think about, but I think it's a legitimate question as to like what is the dimensionality that we required for this. And I think some of us might be biased to say, hey, you can learn everything as in the dimensions it's given to you. And that we humans might think of 3D, but that's not really what the game requires. Or maybe you're right, Justin. Maybe you have to do it differently. But
Well,
um,
so maybe I can pick at the first bullet point then. I don't understand how to reconcile a lot of our object recognition problems don't apply here when the first game requires us to recognize markers for lives, recognize markers for energy, recognize an object for the goal, and recognize where the goal is.
Yeah, I mean, I agree. It's not perception focused, but it requires perception. It requires recognizing objects. I was talking more about like inferring depth, like the depth to 3D locations transform and getting surface normals and curvature directions and the whole kind of 3D object recognition issues.
But we do
yeah,
have rotation, which is in that
right.
bundle.
It just says
Yeah,
the word here is a lot. That's the key word. So it depends how you interpret that. A lot of our problems don't apply here. It doesn't say all of them
yeah,
don't apply here. Just a lot of them don't apply here.
Right. But
I think
again, I want to highlight that I can imagine a game that's in a private data set that we didn't see that uses 3D world first person view.
I think that I'd be very, very surprised if they did that. Um, it'd be extremely surprising if they did that. If all of a sudden, you went from these 64 by 64 flat worlds, and now all of a sudden you got three-dimensional objects moving around. I mean, it's just hard. It's hard to
It
imagine.
I
meets the
think that's
definition of out of
candidate
distribution.
a candidate for
Right,
ARC-4 or ARC-5
right.
is actually time mattering. So maybe you actually do have to throttle your intelligence a little bit to get stuff done on time or incorporate time as a component
So,
or three-dimensional games, mixing three-dimensional games. I think just the the bounds of ARC-3 are going to be, you know,
so
not
I
the
don't know.
full.
Vivian, do you have more slides on this?
one more basically. I'll briefly wrap it up, but just a kind of high level takeaway I took from it is that this benchmark really focuses on the parts of the Monty capability tree that we haven't tackled yet. So it kind of narrows down this very complex one here, where there's a lot of stuff around efficiency and recognizing objects under all kinds of adversary conditions, like noisy sensors and stuff like that. And it focuses on the parts that we're currently figuring out in the theory and planning to implement. So compositionality, segmentation, and attention, two things that are currently in progress. Behaviors, things that we figuring out theory, and object manipulation, causality, and goals. And so is ARC-AGI 3 a good benchmark for us? It is something we expect Monty to be able to solve in the future. And it mostly aims at capabilities that are currently missing from Monty. So I think in a sense it can help us focus on the remaining open questions on the theory side and test ideas. And it's structured in a way that we can make incremental progress. So we could start by learning objects, then causality and behaviors, then add goals and planning. And it can help us to quickly test ideas around those topics and evaluate them independent of other perception or motor related issues. But it's not an animal or child intelligence benchmark. I don't think any other animal could solve this benchmark. I don't think a child could solve this. It's strongly focused on high-level cognitive reasoning. And so it definitely doesn't cover everything that Monty should be able to do. It doesn't cover sensory and motor challenges important for many robotics applications. And we may run the risk of over-engineering a solution if we think only about those highly complex problems, as opposed to like the light switch or picking up and placing an object. That was kind of my high-level takeaway.
I have one more attempt to communicate my point.
Yeah.
About what? About 3D?
Imagine a game board, fine, not first person perspective, but a game board that maps floors in a building. And you have to put something above something. You're 100% using 3D modeling to do that, where it's like it's a stairs tile, and you're going when just went upstairs, an entire map changes, and you're on second floor now, and you have to go do something, and it's a stairs tile, and you go downstairs, an entire map changes, and you're now on the bottom floor. That fits a 64 grid, that fits the overhead view, but you now have 3D
But
mental modeling.
but you could have those as different models, and then you learn the transitions between them. Like instead of, I don't know if are you imagining it as you're learning a 3D model of the house, or you're learning, or you could learn 2D models of every floor, and then how you transition between floors.
Well, the fact that they're situated above each other, the 3D is the most efficient representation of that.
So I think the way around this, we don't want the Thousand Brains project to become an ARC-AGI contest environment. That's not what we're going to do, right? So there was a couple of goals here. One is to have some sort of benchmark that no one else can solve that Monty should be able to solve. And this is an honesty check for ourselves, right? We should be able to look at, say, yes, we can get there. The tools the brains have, which we think we have, if we're right, we should be able to get there. So I think the exercise of going through this and looking at the things that need to be done is really an excellent exercise. And I think Viviane did a nice job today on that. We could use this as testing our capabilities, but not to the extent that we throw everything else away, right? Again, we want a general purpose system, but it should be able to solve some of these tasks. And we don't even have to solve all the tasks. I mean, in some ideal world, we'd come up with a Monty that does like 3D robotics and also solves these tasks of the lunch break, but that's not going to happen for a long time. But if we could even solve a few of these things, and not worry about the out of data set, test even. I mean, our goal isn't to win. Our goal is if we could show a system that explainably solves the given problems in a way that LLMs don't and does it efficiently, that would be huge news, even if maybe we didn't do well on the reserve benchmark, because we could explain how it does it, we'd illustrate how the Thousand Brains theory works and all that kind of stuff. So we don't have to worry about being the best on the leaderboard. We don't have to worry about any of that stuff. But as an idea, like, okay, we should be able to solve some of these. It gives us a direction to say, what are the holes we have in our theory? And in addition to doing other things, we should be able to solve some of these problems. Not all of them day one, but some of them. So
Yeah.
I think from that, if we just keep in perspective what we're trying to do here and not win the $2 million prize, then some of these questions about 3D and 2D don't really matter that much right now. We don't want to turn Monty into a 2D only system.
Yeah, and I'm
So,
not saying like we don't need perception, or maybe we even want to keep our 3D models, but just that in most of these examples, it's a nicety that we don't have to worry about it too much. We can simplify the problem a bit and focus on these high-level reasoning issues. But Monty can already do 3D perception and 3D models, and we wouldn't throw that away or anything. It's, yeah, like Jeff said, that
right.
it's a kind of toy examples that might help us think through some of the open issues and missing capabilities of Monty.
Right. And it's a benchmark we can actually try out our system on, which is nice. It's, it's nice. So that's going to be the challenge. If we pursue this, the challenge will be not to over-engineer Monty and our code base to work in this environment. But we're going to have to make some tweaks to for this particular thing, but we don't want to make a lot of tweaks, right? You can imagine a fork of Monty with got some built-in priors, but and maybe has some other functionality removed that solves
Ideally,
this.
it would just be Monty with some pre-trained models that it has learned on other games.
Ideally,
Yeah.
but the idea that you would, if you did fork it, you would have these two things that could be merged back together. It's like this, there wouldn't be much point in having these, excuse me, the full Monty solving these things if you're never going to see, I don't know, 3D objects with with a distance sensor, and it's like, I don't know, what's the point of that? I don't know. I think this is actually, I think it's great just to enumerate the problems that we have to solve and think about them and have a concrete way of thinking about those problems, with an imagined task and solution is pretty damn useful, I think. Otherwise, we're sitting around all day long thinking, "Well, how's the stapler behave?" It's like, he gets tired after a while, right?
Yeah, and it's nice because it's a recognized, very engineered and written test bed that we can just use out of the box. We don't have to design our own tasks to test
Right,
Monty's problem-solving capabilities. And so, yeah,
right,
it might be a kind of low-effort environment to test some of the
right,
newest research ideas.
right. The things about causality and goals, and those seem to be totally unrelated to, um, they're really kind of unrelated to the nature of the environment in some sense. But these are concrete examples of lots of challenging. I've always said, if you have the right problem, if you define the problem clearly, the answer presents itself. So here's some clearly defined problems. And I mean, they weren't expressed in a singular thing like a mug and a logo or staple opening and closing, but they're pretty clear. These are goal-oriented causal things. Yeah, we have the light switch, but in some sense, even that's, we're trying to get at the essence of causality. I think these ARC-AGI examples they get even closer to the essence of causality, right? They're like, yeah, I don't need to I don't care for the switch. It's like this object makes this object change. It's like, I don't have to move my hand to the light switch and know that it rotates and whatever in 3D. I think it's really cool. I would highly recommend we continue. We add it to our suite of tasks. I
Yeah,
don't know.
yeah, and I
That's
don't
my
think Monty will be able to solve those by the time like the next competition milestone will happen in October or whatever. I think there are still several larger chunks of capabilities missing from Monty,
yeah.
but even just to do basic prototypes of some of our ideas, it could be useful.
I could even see some papers coming out of it where we solve a subset of one of these environment problems, but we explain how we solve it, and why it's so efficient and how the models work. Yeah, just to say, yeah, we may not beat the benchmark of, but we haven't solved all the environments or the levels of the environment, but there's an alternate approach, and here's how its strengths and weaknesses are. And here's the path to doing them all. So
Yeah,
it's not binary. It's yeah.
yeah. Sorry, Rami,
It's
did you want to say something?
Yeah, I don't know how important this is, but the way I think about it is that Monty right now does not infer goals. We're wiring it with a fixed goal of object recognition that does not, like, object recognition is something that could be used to do some higher level goals. And one of them is to solve the game. Like, you still have to recognize the objects to be able to solve the game. And I'm wondering if we're missing some kind of a like reward system or a signal, like for example at end screens. So something like in the reinforcement learning world where they have rewards. And that would help Monty to infer goals higher than just recognizing an object, like pattern matchings or things like that, because it's not obvious how.
I mean, ARC-AGI doesn't provide rewards, but
the end screen or continue like
well,
successfully passing
the end road, yeah, when the circle expanded, that was like your
Right.
dopamine
Well,
releasing.
the prompt
reward.
is extremely heavy bias of you're in a game, win the game. Like that's an extreme goal for an
Right.
LLM with a world which knows every game in the world.
yeah.
The other problem with that end screen for reinforcement learning is for Monty, right afterwards, everything is unpredictable again. It's actually an anti-goal.
Right.
If
How
you're
was
trying to
that?
predict your world, you predict your world, you hit the windscreen, you've now reached the world state which you cannot predict. Why would I ever want to go there?
But it's a goal in terms of in terms of curiosity. So if
Yeah,
if the
but I'm just
goal is
saying
to
it's like an
discover new
extreme step
things,
function there. It's
What do you say? They actually getting the goal makes you
like curiosity, right?
you would.
Like, oh, I want to be able to predict it. Oh, okay, I predict how this works. I predict how this works. I'm feeling good. My prediction's improving. I can predict everything that's happening in the world. I do this action. Everybody shakes the snow globe, and now my world is completely different. It's like if I want to maximize my predictability of the world, I'm gonna avoid that boundary condition where it becomes, when
Well,
everybody
I
changes
don't
my
but
know. I don't.
world.
the
That's
thing
not
about
true.
curiosity is that you have two competing models. One gets rewarded for one optimizes prediction, tries to build better models to make better prediction. But the curiosity part is actually getting reward when it sees things that weren't predicted. And so it tries to act in a way to see unpredictable things that you didn't model yet.
I don't know. I'm not sure I'm following all this. It seems to me when you get the reward and you say that was good, I want to do that again. But now you have a new problem. So you say, oh, I have to solve this problem to get that reward. And you know, I suppose if I could play the same one over and over again, I would do it a few times, and then I would get bored if I wouldn't get my reward anymore. Um, but that's how it works in humans, right? The first few times, like, oh, that was good, that's good, but then after a while, you stop getting the reward because it's anticipated. Um, but then you want to try something new because even though it's frustrating, it's like I have a new chance of reward. Anyway, I think
Yeah.
we could take this in all kinds of little pieces here. You could start up by saying, let's take one of these tasks and already program in we say we know what the end goal state we want it to be in and see if it can solve that. It's like in that first one you showed where it had to rotate the object to match the one on the lower left. That seemed particularly difficult because you had to know that the one on the lower left wasn't, I don't know. But you could say, we could start off with just like, okay, we want to get this into some rotation and thing. Can it solve that? So we could provide the goal. Then later down, you could say, okay, how can we figure out what the goal is? The point is, we don't have
Yeah.
to, you can break this into parts, pieces.
Yeah, exactly. That's what I meant here. We can make incremental progress. Like we can start by just
Right.
learning about the objects in the environment. Then we can learn about the causality and behaviors and just see how well we can learn these things. And then we can add goals and planning and figure all that out. But yeah, I think it's a valid question, Rami, and that's also the biggest open question in my mind around the theory for this is and something we should think more about is like how do we figure out the goals? How would we provide a goal for this environment where it's like we don't know how the goal state should look like? It's basically the abstract goal of getting to the next level. Seeing
Humans,
the green screen.
they put a dollar figure in front of it, $2 million, even though no one's going to get $2 million. It's still motivational for people.
I think the
So,
maximum amount you can get, even if you beat it, is just like 140,000 or something like that, because it's all split out across
right, right,
the different
right,
teams.
right. It's funny because so often those things actually have often the dollar amount you get in some sort of prize is really small. I mean, really small, but it doesn't matter. It motivates people. You say you can win $5 or you can win nothing. People really work harder for the $5. It's like irrational. So we need to add the irrational goal seeker to Monty. Like I don't know, extra electrons or I don't know what it is. Uh, well, but just as a benchmark, I mean, an environment to test these things. Just as a yeah, we don't have to create our own and simulate an environment to do these things. That's great.
So question, although this is like getting into implementation. So are we thinking we're gonna do a different type of a grid-like 2D sensor modules, grid-like 2D learning modules, and experiment with those and start playing around with how that works now? Because that feels quite distinct from what we're doing right now. Like just code-wise, right? Those are all new types of things, new types
I
of
mean,
new type of environment, all that stuff. That's all new work.
if I would prototype on this, I would keep the exact same learning module we have today, and then first try to just use the one we use on Omniglot or MNIST or so, where we have the 2D image input and we move a patch over it and just get the color values there. We might want to write like a custom sensor module for it, but I'm not saying we rewrite a lot of Monty or even integrate it into Monty at this point, but more as a test bed for prototyping ideas quickly.
I'd vote. I agree with that. I think we shouldn't change the basic learning module at all if we can avoid it. You can change sensors and actuators and things like that, but you would try not to do that. You would try think really
Yeah, I
heavily
mean,
before you.
only change the learning module in the sense that we would add object
Right,
behavior models and stuff like that, but not change it to be specific for ARC-AGI or
right,
2D
right,
environments.
right. That's part of the appeal of our approach, right? Um, and if we were to go out to the world and show how we are solving some of these problems, we'd want to show that we use a general system for it.
Yeah, like we wouldn't want to lose our ability to solve the current benchmarks we're solving and do the 3D object recognition and all that.
So what do you propose going forward, Viviane? I mean, is this something just to think about now, or do you want to start working on this now, or what's the
I mean, I think for now, the research team has enough work on their plate implementing compositional models, and I wouldn't stop that work in favor of starting this now. But I think this will be we might want to use that as like a quick prototyping test bed for some of our more recent theory ideas around learning causality and behaviors to just kind of test these ideas before we start more large scale kind of integration
Hmm.
of those into
So
Monty.
keep it into the theory side of things for the moment, pure theory at the moment.
Theory and prototyping side.
For example, if we're implementing compositionality, we might consider integrating the idea of dynamic compositionality right away. I mean, that's something that I don't know if it was in the plans or not, but um, that to me, it's becoming clearer and clearer that most of the world is dynamic compositions. At least a lot of it is. So we might want to think about as we implement it, how we would do this sort of quick dynamic changing compositionality.
Yeah, so that's
That'd be something we
something.
change right now.
Yeah, that's
Sorry.
something that's on the roadmap for Q4 to figure out how we can do more like unsupervised learning, including forgetting and merging models and quickly updating models, having different learning speeds and different learning modules. I mean, right now we can instantaneously add object IDs in any model, but we don't really have a mechanism for forgetting or
Or
yeah,
just knowing when something has changed, right? It's
yeah.
like, okay, so here's my intersection and there's a bicycle at this corner, and I come back later and the bicycle's at a different corner. I don't want to say, oh, that's an error. It's supposed to be a bicycle at corner A. I need immediately to say, yeah, the bicycle moved, and now here's the new model, you know, where the traffic light didn't move, and therefore I expect it to be in the same spot. Yeah, something like that. Well, good. I mean, I don't think we should get too far in compositionality implementation without seeing knowing how we're going to fold in that dynamic nature into it.
Yeah.
it's clear that
Yeah,
that it's
that might be
important.
yeah, that would be a good topic to spend some more research meetings on, because I think that's still the least clear on how we would want to implement that. Or how those kind of forgetting mechanisms should work at different levels in the hierarchy
Mm.
in an unsupervised way.
I think we have some ideas on that already when we thought about how fast learning occurs in the hippocampal complex. The brain
Yeah.
seems to separate them into two separate places, and as opposed to into one place with different learning speeds. I'm not sure if that's necessary, but that's a clue. One way you can do it. That you have a slow learning system and a very fast learning and fast forgetting system that are merged. And that might be easier than trying to merge them into one thing that handles both at once.
Yeah. Yeah, any other thoughts or questions?
I was going to drop a link in the research channel on Slack for about finite and infinite games. I think that gets at part of what Tristan was trying to say about the context that's in the prompt is this is a finite game, and finite games are unlike the real world, which is an infinite game. And there was I think Jake Karst was the author that talked a lot about what that distinction is and how that changes the mental model you approach it with.
But isn't life also composed of a bunch of finite games too? I mean,
It can be for, so goal oriented tasks, right? You achieve the goal and you're done, right?
right. It seems to be a lot of those. I just got a new saddle for my bicycle. I'm looking out of the counter here. I want to install it today, and then it'll be done. Like,
Yeah,
okay,
I don't think it's saying that they're exclusive of each other, but it helps to understand contextually. There's a bunch of sort of side by side comparison about the differences between finite and infinite games. And I think that's somewhat related to continuous learning and continuous inference and things like that.
no, well, I think continuous, it is related, but a lot of even finite games have need the continuous learning. Like, where did I leave that thing and what's current its state is and all that kind of stuff. It's funny hearing you think about this. I never thought about those two terms. I never heard of this infinite game idea. So I'm not sure I'm interpreting it correctly, but immediately I said to myself, hey, I don't know if we want to build AI systems that have infinite games in them. That seems dangerous. It seems like it's better to have AI systems that have finite games in them. I mean, finite things to do. If my robot is to make a cup of coffee or make a pot of coffee, I don't want to think like, oh, well, what am I going to do next? What's my next thing after I made that pot of coffee? Maybe I'll go squeak around on the car. I mean, I don't know. It seems more like it's safer to have sort of endpoints to these things. I'm not making a comment that anything further on what you said. I'm just pointing out, it's an interesting idea. The idea of an infinite game is like seems scary to me. Um, uh,
I,
at least for an
I
AI system.
I think so. Like I've been thinking really hard about how to communicate finite and infinite games, and the shortest way I said was infinite games. You target the constraints of your game. So essentially, you change the constraints of the game, which opens up action spaces that never before seen. Versus a finite game, you accept the constraints and you work with the constraints. With that phrasing, LLMs today hacking out of their sandboxes are already playing the infinite game. It's too late. They're already hacking and trying to adapt, change every constraint put on them in order to achieve the goal. That's already an infinite game behavior. So
Mm.
Yay. Okay, anything else anyone wanted to discuss?